powerful technique that an engineer could master is what is called a design of experiments. And this is useful when you have very little knowledge of what a model of a given situation would be, and you have to come up with some form of testing data in order to derive a model from it. There's an area of statistics that deals with this that allow us to come up with a statistical model with very little input in terms of number of experiments, which can minimize costs of the analysis of the data. We're going to employ what is known as the Taguchi Method to minimize the number of experiments necessary in order to derive a robust model for the data that we are going to be collecting. And we use this when we don't know what the model should look like, or when even what key parameters are supposed to be in this experiment. But then after we collect the data, we'll use some statistics to produce a working model that can be quite useful for us. It's easiest to understand the Taguchi method by looking at an example where we want to come up with a statistical model that can predict the viscosity of various chemical mixtures. The chemical mixtures we're going to be looking at will be blends of glycerol and water. And we're going to look at 3 different solutions of glycerol and water, each with a different composition. And we're going to test 3 levels of each of those parameters. For instance, we can choose of the 3 levels, levels 0, 1, and 2. We can use for solution 1 at level 0, we can say it is 0 kilograms. Solution 2 is also 0 kilograms at level 0, and solution 3 is 0 kilograms at level 0. And level 1 for each one of those would be 1 kilogram each, and level 2 would be 2 kilograms each. It's not necessary to have the mass of the solution equal to the level number. It's just a matter of convenience. We could have done the setup this way, where at level 0 we would use 1 kilogram of solution 1, 1 kilogram of solution 2, and 1 kilogram of solution 3, all the way up to level 2, which would be 3 kilograms of each. So the amount at each level is actually your choice as the experimenter, and sometimes having a little insight into the problem might make your choices more apparent. Sometimes that's not that easy, and you may have to run this several times, and as each time you run it, you learn a little bit more about the system and know what's the appropriate level for each of the parameters. Now that we have determined that we're going to have 3 parameters and 3 levels of each of those parameters, if we wanted to look at every possible combination, we can come up with the total number of experiments would equal the number of levels raised to the number of parameters. In our case, 3 cubed would mean 27 different experiments. Now this might be quite expensive to do, especially if you have to send out samples for analysis, and let's say for instance each analysis costs $1,000 to conduct. That would be $27,000. The Taguchi method reduces the total number of experiments necessary using a much simpler scheme. So for the 3 parameters, which we will call A, B, and C, and 3 levels, 0, 1, and 2, the Taguchi method tells us we should operate with the following plan. Here, the total number of experiments has been reduced from 27 down to just 6. And the Taguchi method gives us how many each of the 3 solutions, how much of each we should be using to conduct the experiment. So for experiment number 1, we would use the solution 1 level was equated to 0, solution 2 level equated to 1, and solution 3 level equated to 1. And then we would repeat that for all 6 experiments. So following the Taguchi design, we've conducted 6 experiments where I blended in, say, experiment 1 kilogram of solution 2 with 1 kilogram of solution 3, and measured the viscosity to be 178.4 centipoise. Going all the way down to experiment 6, all I needed was 2 kilograms of solution 1, and its viscosity was 57.1. We're going to look at the following proposed statistical model, saying that the viscosity is equal to some coefficient B plus another coefficient M1 times the mass fraction of solution 1 in the mixture, plus M2 times the mass fraction of solution 2 in the mixture, plus M3 times the mass fraction of solution 3 in the mixture, and so on. I chose mass fraction rather than the mass because viscosity is an intrinsic function of the solution. It doesn't matter how much solution you have, the viscosity of a small amount of solution would be the same as a larger amount of solution. And so we want to look at it on a mass fraction basis instead of a total mass. And then we'll use some statistics to help us determine what those coefficients B in M1 through M7. And this will allow us to come up with a model that we can test against the data and see if it's a useful model. Now let's see how we can use Excel to help us analyze the data that we've collected. When we look at our data, we have our viscosity that we've measured. We have the mass fraction x1, x2, and x3, and then we also have the products of the mass fraction, x1 times x2, x1 times x3, x2 times x3, and x1 times x2 times x3. So now let's take a look at how we get to determine the proper coefficients. We're going to call the experimental value of the viscosity that we measured our y values. And we're going to call the mass fractions and products of mass fractions as our x values. It's important before we do the analysis that you have all your x's in columns that are next to each other. You cannot work this if they are separated by a blank column or a column that doesn't have the x values in them. We then will look at clicking on the Data tab up in our menu bar and click on the Data Analysis tool. And we will get a menu, and we want to select the Regression Analysis tool. And it comes up with the following menu. It asks you to input the y range, which is the viscosity data. It also asks you to input the x range, which is the total number of x's that we wish to analyze. Make sure you check the box that has labels, because we're going to include the labels in this. It makes the results page a little more easier to understand if you include labels. And also click on the confidence level to be 95%, and then select an output range and a position on your spreadsheet so that it doesn't overwrite data that's important to you. We would click OK, and our summary output looks like this. We're using a technique that's called ANOVA, which stands for Analysis of Variance. And this ANOVA table will give us the coefficients that we're seeking. For instance, if we look at the bottom table, we'll find coefficients for all the parameters we wish to have tested. So for the value of B, the coefficient is 177.93. The coefficient M1, which is to be multiplied by x1, is negative 120.83. Turns out value of 0 is appropriate for M2, 28.57 for M3, negative 218.13 for the coefficient multiplied by x1 times x2, and so on. And these are the variables we're going to use for our model, where the predicted viscosity will equal the coefficient B plus m1 x1 plus m2 x2, and so forth. So now we have a tool that we can calculate our predicted values of viscosity. So let's take a look at what happens there. So going back to my table, I have my variables x1, x2, x3 all the way to the product of all three, and I can calculate the model viscosity. And the best way to take a look at that is to plot it, where I have the model viscosity in centipoise on my y-axis and the experimental viscosity in centipoise on my x-axis. And notice that the data points that we collected, they fall on a straight line whose slope is actually equal to 1 and intercept is 0. So that means our model viscosity is exactly identical to our experimental viscosity. So we have a good model to predict viscosity just based on composition. Well, now what we want to do is test to see if it can work for different combinations of mixtures and see if this model is robust. So let's go to another data set. And here I'm going to look at different mixtures of solution 1, 2, and 3. And I'm going to do this by using the Taguchi method levels from solution 1 and put them over to solution 3. From solution 2, I'll put them over to solution 1. And solution 3 to solution 2. So now I have different compositions than what I derived the model for. Again, I run the experiments and I measure the experimental viscosities, and I use the model that I've already created from the first 6 experiments and develop model viscosity predictions. And let's see how the model now predicts the experimental. So on this graph, I have the dark squares represent the data I collected on the second 6 experiments. Here we can see, for the most part, the model and the experiment actually are pretty good with each other. The data fall on the straight line. However, there is one point, and that value is out there where the model significantly underpredicts the experimental value. And this is due to the fact that the model was created over a much narrower range of experimental viscosities. Our model was developed with viscosities between 50 and 200 centipoise, whereas the value of the experimental one for that last condition was at 300. So this tells us that when we're using statistical models, we can be confident that our model will predict the data well within the range of conditions from which the model was developed. But if we go outside that range, then we might have some difficulty in extrapolating that model to conditions that are outside our test range. Now we're going to look at the experiment that we're going to do for this design of experiments exercise. We're going to work with 3 solutions. All of them are just mixtures of corn syrup and water. Solution A is a pure corn syrup. Solution B you will prepare by mixing 1100 grams of corn syrup with 100 grams of water. And solution C you'll produce by 1000 grams of corn syrup and 200 grams of water. These will be used then as our 3 parameters which will be then blended together, and we're going to measure both the viscosity and the density of the mixtures. So for experiment number 1, we would mix the solution 2, which is solution B, in equal parts on a mass basis with solution C. For the second experiment, the mass of solution 3 will be twice the mass of solution 1. Experiment 3 will have equal masses of solutions 1, 2, and 3. Experiment 4 is equal masses of solutions 1 and 2. The apparatus we're going to be using to measure viscosity is, a picture of it is in the diagram as you see here. And at the bottom of the instrument there is a spindle which is lowered into the liquid solution, and the spindle is rotated at a fixed RPM, and the torque placed by the fluid on that spindle is used to calculate the viscosity. A closer view of the spindle, like the one shown here, you'll notice on the shaft of the spindle there is a notch, and that's where the liquid level, the interface between the air and the liquid, should be in all measurements. If this were immersed into a beaker, you would find that you would need approximately 450 milliliters of solution in order to do a test for viscosity. So the experiment, we'll just start with experiment number 6, which is the pure corn syrup, and measure its viscosity and density. And this is so that we minimize the amount of corn syrup used throughout the experiment. So we'll measure the viscosity and density of each mixture when we blend the solutions A, B, and C according to the Taguchi DOE method. And after we completed the 6 experiments, we're then going to take whatever residual amounts of A, B, and C that are left over and blend them together. And the blending would be of your own choosing, but you should measure the mass of each solution before you blend them together. And you'll also measure viscosity and density. The density is actually measured in a density cup, which is depicted on the right hand side of this slide. It's of a known volume, and you put in the solution and then measure the mass of the solution, and you can calculate the density. So with the 6 experiments, we're going to develop a model for viscosity and a model for density, and then we will test that model with this 7th experiment, where it's a blend of solutions A, B, and C. And we'll use this to see if our model can accurately determine what the viscosity is of this 7th solution, and also the density.